The application of electromagnetic induction in sensor-based tracking system offers a simple yet effective approach to detecting motion and positional changes. These basic principles of electromagnetic fields induce a voltage in a secondary coil through a varying magnetic field produced by a primary coil. When electricity flows through a coil of wire, it makes a magnetic field. If this field changes, it can create electricity in another nearby coil. The main idea is to create a changing voltage in a coil placed inside a screwdriver, which makes a changing magnetic field around it. A secondary sensor coil is positioned on a finger and responds to the magnetic field changes by generating a voltage. The induced voltage in the sensor coil varies based on the distance and relative orientation between the two coils, enabling real-time positional tracking. How much of electricity appears in the sensor coil depends on how close the two coils are and the direction they face. If they move or turn the direction, the voltage changes. This concept mirrors the electromagnetic tracking technology used in image-guided surgery system, where real-time position detection is critical.
Hello, I am Basim Mudassir from ENT section 14, group 4. I am going to explain our experiment of electromagnetic imaging and tracking. First, here we have a coil wrapped around a screwdriver. This will produce an electrical field. This is a direct application of Ampere's law, and if the voltage applied is an AC voltage, it will generate a fluctuating magnetic field. This is the first piece. The second piece is another set of coil that we will measure the voltage induced on it due to this electrical field. Okay, this is all done by using an STM microcontroller. The STM microcontroller is connected to the laptop, and we are going to measure the voltage induced in this coil without the application of the electrical field. See, the electrical field is not applied. We see very minimal values, 2 millivolt or 3 millivolts, very minimal value. Now we are going to apply the electrical field. Notice the spike. It has gone from 2 millivolt, 3 millivolt to 1 millivolt, 1.6 volts, and so on. If we move the coil, we will see a different reading. See, it has gone from 0.16 to 0.17, and in theory, all these changes can be used to mimic directional changes in the position of the coil.
Now, I will briefly explain how electromagnetic field theory is applied in voltage detection and tracking system using coils. First, let's start with voltage detection. When an alternating voltage is applied to a transmitter coil, it generates a time-varying magnetic field. This is explained by Ampere's law, which states that electric current produces a magnetic field around it. Since the voltage is alternating, the current also changes the direction continuously, and this causes the magnetic field to vary over time. Now, according to Faraday's law of electromagnetic induction, a changing magnetic field will induce a voltage in any nearby coil, in this case, the sensor coil. So, as the transmitter coil creates a changing field, the sensor coil detects this field and a voltage is induced in it. What's interesting is that the amount of voltage induced in the sensor coil is not always the same. It depends on three main factors. First, how far the sensor coil is from the transmitter coil. The second one is the orientation or angles between the two coils. And lastly, the strength of the magnetic field produced. This principle is actually used in real-world systems like image-guided surgery. In those systems, small sensor coils are embedded in surgical tools. As the tool moves, the system detects changes in the induced voltage and uses that to track the position and orientation of the tool in the real time. It's quite similar to how MRI uses spatial encoding to locate body tissues.